Okay, so this is the first problem we're going to work in class. We're trying to write equations for shear force and bending moment. You'll notice that I indicate where x is. So we're not going to cut it at some point like we did before, 5 feet or 10 feet or 12 feet. We're going to cut it at x feet. So again, that's where my cut's going to occur. And I have to now start thinking to myself, do I want to work with the left-hand side or the right-hand side? Let's look at the right-hand side just for discussion purposes. As we talked before, you can see it's a trapezoidal load. So I'm going to have to break that up into probably two forces, or two sections. A uniform load and a triangular load. So I have two forces to keep track of. Now when I'm figuring out the area of this particular structure, what's this distance right here? Yeah, so the total distance is 20, and I'm cutting it at x. So this distance here is going to be 20 minus x. So that means that when I find the areas underneath this curve, which will, of course, will relate to the forces, they're all going to be functions of this 20 minus x. So you can see that's going to be kind of a little tedious to deal with. You can do it. You've all had courses in algebra. You can do it. It's just, why if you don't have to? You look at the left-hand side, it's just a function of x. Now what do you have to pay for with that is you have to know the reactions at A. So I'm going to go left because I think that's going to be a lot easier to deal with. But in doing so, I'm going to have to find the reactions at A. So let's do that first. So I'm going to come over here and I'm going to draw a free body diagram for our structure. The concentrated equivalent force for the whole structure, since it's a triangle, is going to be 1/2 the base times the height. It's going to be located in the centroid of the triangle. So 1/2 base 20 times height 2 is a force of 20. From A to the centroid is going to be 2/3 of the distance, and 2/3 of 20 is going to be kind of a funny number. So I'm just going to take 20 and multiply it by 2/3, which will be 40/3. Okay? That way I don't have to deal with the fraction right now. You see that? 40/3 from A to the centroid, 2/3 of 20. And then what I'm going to do is I'm going to come over to A. Now, since I'm writing equations for shear force and bending moment, I want to draw the positive values for shear force and bending moment. Shear force on this left edge, positive, is it up or down? It's up. Why is it up? Because it's going to try to push that edge this way, which is clockwise. What's the moment here? Well, positive bending moment looks like that. So there's my positive bending moment on the left at point A, and positive shear force at point A. Okay? You can see that when I do the equilibrium of this particular problem, it's not going to be that tough. So I'm going to start with summing my moment. So I'm going to assume right-hand rule for my sign convention. Make sure the whole structure is in equilibrium. So with right-hand rule as my sign convention, this moment is positive or negative? Negative. About A, this force is positive or negative? It's going to create negative moment. And that'll be 20 kips, and the distance from A to that force is 40/3. So I should be able to solve for the moment at A. It's going to be negative, and whatever 800 divided by 3 is, 266.7, is that right? So 266.7, and that will be kip feet. Now, does it make sense that the moment at A, the bending moment at A, is negative?
Why do we assume clockwise?
Oh, for the shear force? On the left side, it's going to try to push the structure this way, right? So you notice that it's rotating clockwise. So that's our sign convention. Anytime your object wants to rotate clockwise, that's positive shear.
So if you would get it at B, it would have been down.
It would have been down at B. So if you look at this structure, you're probably going to guess that it would deflect something like this, which is kind of a big frown. So you would expect the moment to be negative, that negative curvature. So that's good. Now what about shear? Well, let's sum forces. So I'm going to sum forces in the y direction to find shear. And I'm going to assume that forces that act up will be positive in my summation. So this force is up, positive. This force is down, negative. So the shear at A is 20 kips. Positive shear. Any questions about that? Okay. So now I'm going to cut the structure. I'm going to blow this up so it'll be a little easier to see. So I'm going to cut the structure at this segment. So there it is at some distance x. I've got a triangular load, and I've got the values that I've just determined. So my moment is negative. So which way is negative moment on this edge? That's positive. I have a negative sign, so it's actually in this direction, right? 266.7, and that will be kip feet. And my shear is up, and that's 20 kips. On the cut surface, I will assume positive shear. This is an interesting idea. You can see it here. This is also positive shear, and this is positive shear. You see that combined, they're causing the structure to want to rotate clockwise. And then I'm also going to assume positive bending moment. So our next step is to get a concentrated equivalent force for this distributed load. So what is the force? Well, it's a triangle. So it's going to be 1/2 base times, height. What's the height going to be? What's the height right there? What is the load right there? Well, this is where I think you're going to have to go back and look at the slope and write an equation. So go back to the original diagram, you'll see what's the slope of this line. Well, rise 2 over run 20, that's a slope of 1/10. And you'll notice that starting here at x equals 0, it has no value. So the function should be x over 10. And that will have units of kips per foot. So can I check that? Sure. At x equals 0, I should have 0. And at x equals to 20, 20 over 10 is 2, it matches. So it's a linear line. You only have to match it to 2 points to make sure it works. So we've matched it at both endpoints. So this should be valid at any position x. So now what does my force become? Well, my force becomes 1/2 base x times height x over 10. So you do a little work here, that's x squared over 20. What's the distance from the cut surface to the centroid of the force? Well, for a triangle, it's always 1/3 the distance. What's the distance? X. So this distance should be x over 3. So a little more work you have to do with the variable distance. When you're done, again, like I mentioned before, that's most of the problem right there. Now you just apply equilibrium. So I'll start with moment, like we always do. So summing moments about the cut section. And make sure it's in equilibrium. What do we have? As my Valentine's Day gift to you, I'm now going to start calling on you individually, because I think it's more fun that way. Don't you think so? Should we start in the back or the front? I'll let the people in the front pick. Oh, the front picks the front? Okay. Mr. Brown, since you're in the front. Some moments about the cut.
So, M.
Correct.
And plus 1/2.
This force?
Yes.
Okay, that force is going to be x squared over 20. That's the force. What's the moment on it?
It's over 3.
Correct.
And then
I'll let you off the hook. Mr. McBride, what's next?
then you'll have 20 kips.
Is that going to create positive or negative moment about the cut?
Negative. The moment arm is X, right?
Correct. Mr. Street, what do we do with this thing out here at the end? This moment? You add it. Is it a positive or negative moment with this sign convention? It is positive. And just so you remember, I'm going to put a bracket around the whole thing, because each term looks a little funny, but they all end up with units of kip feet, because they're moments. So all I have to do now is solve for m. So I'll do that. M, which is now a function of x, is going to be equal to, I just have to move everything to the other side of the equation, so it's going to be minus x cubed over 60, that's the first term, plus 20x minus 266.7. And that will be kip feet. So there's my equation. Do you know the bending moment anywhere in this structure? Do you know the bending moment at A? What is it, Mr. Drum? Do you know? We solved for it, didn't we? It's negative 266.7. If I put in x equals 0 here, do I get negative 266.7? So I know the bending moment at x equals 0 should be minus 266.7 kip feet. Is that true? Does my equation give me that? Yes. Check mark. Green check mark. I like that. Do I know the moment anywhere else? Somebody said yeah. Who said yes? B. That's right. What is the moment at B at free end? 0. So that means that my equation, if I plug in x equal 20, should give me 0. Does it? I can't do that one in my head. I have a feeling the answer is yes, so I'm going to begin to start checking it with green. Waiting for confirmation. And yes, Mr. Pham says yes, I like that. So this problem is almost self-checking. If it doesn't check, then what do you do? Not completely. You do have to go back. You would probably go back and review what you've done here. Make sure you haven't made an error. If you like that, then go back and check your equations. Possibly a sign. Am I blinking or are you blinking? Is that me blinking? Okay, so now let's find the shear. So shear is vertical, so I'm going to come over here and sum forces in the y direction. Make sure it's equal to 0. So let's see, who did I leave off on? Sorry, Aga. What do we do? How do we sum forces in the y direction for me? Start on the left side.
Negative v.
Negative v.
Plus 20.
Plus 20. What else?
And negative x squared.
Right, right. This guy here, which is negative x squared over 20. And these will all have units of kip. So all I do is solve for v. So when I solve for v, which is also a function of x, it looks like I'm going to get minus x squared over 20 plus 20. Do I know the shear anywhere? The answer is yes. What is the shear at A, which is x equals 0? What's it equal to? We solved for it, right? 20. Does my equation give me that? When you plug in x equals 0? It does. Do I know the shear at the free end? I do. What is it? It is 0. Does my equation give me 0 when I plug in x equals 20? I can do that one. The answer is yes. I'm feeling pretty good about this. There's one more thing that we're going to not derive right now, but I want you to notice is there a relationship between the moment and the shear? Think about Dunn-Hall. It looks like the derivative. It looks like if you take the derivative of the moment with respect to x, you might get the shear. Right now, that is a purely empirical relationship. I will tell you that later we will derive this, and it is true. So that's another check. If you don't have these little guys to help you out necessarily, if you take the derivative of the moment, these are usually polynomials, so the derivative shouldn't be too challenging, and you don't get the shear that you got here, then you have something's going on. Typically, the shear equation is easier, so it'd be kind of more indication that maybe you did something incorrect in your moment expression. So all I'd have to do now is plot these two things, and I'd have variations of bending moment and shear force throughout the structure. By the way, where is the maximum moment? I will warn you that a cantilever structure is a little unusual. You could plot this. We already know that at 0 it starts off at negative 266, and at 20 it goes to 0. So which of the two of those is bigger? Okay, first of all, sign is not an indication of magnitude, it's direction, right? So looking at the number, it looks like 266 is the bigger number. So that's probably the biggest moment, which just happens to be at the fixed connection. That's typical for cantilevers. So if you had to design this build B, you would have a lot more bending capacity here, and it could literally taper to no bending capacity at B. So if you've ever seen beams that are cantilever that are tapered, the reason they're tapered is because most of the work is being done here, and as you move towards the end of the beam, less work is being done, or less bending capacity is necessary. Little aside there. Any other questions about this one? Okay, I'll stop.